Now we'll start building a baseline MLP model. We'll keep the baseline model very simple. We'll only put basic things here. And to do that, we are going to build the model using the sequential class in TensorFlow. This class is this class makes model building quite easy. Why it is called sequential? Because the sequential class allows us to build model in which the layers are stacked only sequentially. If your if your network architecture is more complex, in which the layers could be stacked both sequentially and some in parallel, then we'll have to use some other approaches available in TensorFlow. But for our purposes now, sequential approach suffices, and due to its simplicity, we are going to go ahead with sequential. So in line 1 here, when I initialize my model equal to sequential, it is like having an empty canvas ready. Now on this empty canvas, you can pretty much paint anything. You can draw any type of network you want to. Of course, under the limitation of sequential that it has to be a linear structure. But you have to respect some necessary requirements. One of them is you always start with defining the input layer, which we have done here. And the only requirement in this input layer is you tell what is the shape of your input. And the shape of the input is, we recall figure 3.2 of the book. In that, the shape is essentially the number of features in your input sample. And that is what we have put here. I recommend you refer to figure 3.2 in the book while we are building this model. So input layer, you just tell the shape of the number of features in your sample, which we have set to n features here. Now we can start our painting and use our imagination. When you follow these rules of thumb, you will get to a reasonable starting point. So as a rule of thumb, what we do is we stack two hidden layers, as you see here, and the size of the hidden layers is chosen from geometric series of 2. Geometric series of 2, we have numbers 1, 2, 4, 8, 16, 32, 64, 128. Basically, that's just the powers of 2. And we have to choose a number from this series which is closest to the half of the size of input sample. For the first hidden layer here, the size of the input sample is equal to n features, and n features in this case is somewhere 60, somewhere in 60s, I think 69. Half of it is close to 34ish, and the number closest to 34 in that geometric series of 2 is 32. So I chose the number 32 here for the first hidden layer size. And for second layer, it becomes easier. I just take the half of the size of the previous layer because the input to this sample, the input to this layer will be of size 32. So I choose 16. And then for the last layer, the size of the last layer in this case will be 1 because we have a binary classifier, so the number of classes is 1. If it was a multi-class classifier, then you will set the size will be equal to the number of classes. Then talking about the activation function, again, the rule of thumb is to use ReLU activation for your hidden layers. And for the output layer, it depends on the problem. Here we have a binary classifier, so we should use sigmoid. If it was a regression problem, we would use linear because the value of output could be anything, any real number, I mean. And if it is a multi-class classifier, then we use, I believe, softmax. Then I look at the model summary uh, just to get a feel of how my network looks like. This is just showing the shape of your outputs from each layer and the number of parameters. It is good to have a look at the number of parameters in your model and the shapes here, whether they are all looking compatible, and whether your model has become too large to handle or not, given your data size. Things look reasonable here, so I'll move forward to the model compile part. Model compile, I have few necessary arguments, which are optimizer, loss, and metrics. We again have several choices for optimizer, and why don't we look at our choices? Let's go to TensorFlow. I'm on the TensorFlow page, and I'm looking at the choices of optimizers here. As you see here, we have Ada Delta, Ada Grad, Ada Max, and so on. Now, not all of them are applicable on all models. Some of them are generic. For example, Adam is one of them. SGT is also quite generic. But among all these choices, my preference and recommendation is Adam, because Adam is relatively insensitive to its hyperparameters. Also, it is quite robust for non-convex problem optimization, and deep learning is the epitome of a non-convex problem. And generally, Adam works better than other available choices in terms of convergence. So my recommendation is go with Adam as a rule of thumb. But of course, you can then iterate and try others for improvement. For loss, just like the optimizer, you can go to TensorFlow web page and see the choices for loss. We have a binary classification model for which binary cross entropy generally works best. So it is recommended here. And matrix, we discussed in the previous chapter, in chapter 1, that for the imbalanced problems that we have in hand, the traditional accuracy measure may not be the best thing to use. Instead, we want to use recall, F1 score, and false positive rate. Now, if you see here, we have recall, which is present in TensorFlow by default. And if you're wondering why I wrote here the whole address of recall, if I do not want to do that, I can import recall at the top here by giving the complete address. But sometimes I just get lazy, and because I have anyway imported TensorFlow keras, I just use this relative path. It's up to you, your choice here. And if you wonder how to determine what is the path, you go to the TensorFlow webpage and look at the path. So here I am going from tf.keras. From tf.keras, I'm going to go into matrix, and inside matrix I have recall. So the path becomes this entire root, tf.keras.matrix.recall. You can see it here, so this is a complete path. So you can just put it here. I sometimes do that. And then we have other two matrix, F1 score and false positive rate. These are not present in TensorFlow, so we have custom defined it. It's in our UDF. And we will look at these UDFs more closely in the next part. So I did the model compile. If there was anything wrong, I would get an error here. And I did not get any errors, so I'm moving on to the final part of this modeling, which is fitting the model or training the model. Model fit requires a training data. Here we have provided a scale X and the training Y. The batch size, it's another hyperparameter. The recommendation is to choose batch size from the geometric series of 2 as well, because model fitting is generally not sensitive to minor differences in batch size. For example, choosing between 100 and 101 makes no difference. So look in this geometric series of 2 and see a number that looks reasonable. In this case, I chose 128. People many times use a smaller number because smaller number makes the model training faster. If your data set is huge, it is preferable to use a smaller batch size that will make it quicker, the model training quicker. But because we have imbalanced data, if I set the batch size to be very small, people typically use 16 or as small as 16. But if I do that here, it is likely that that particular batch may not have any sample, any positively labeled sample. So to increase the chances of each batch having at least one positively labeled sample, I've set it to 128. This is in the baseline. You can also uh, choose other numbers to see if that works better for you. Epochs is a number that you think will be sufficient for your model to converge. It is difficult to know ahead how many epochs will be best. Uh, you start with some number of epochs and look at the loss function, the trend in loss function, and if you see that has stabilized, you're good. If not, then you have to increase the epochs. So now we will fit the model. The model fit is complete. Now we will plot the results. For plotting, I have created a custom function. You can plot directly as well. Because I have to do this plotting multiple times, I chose to write a custom function that I can reuse over and over again. When I did the model fit, I stored the model fit output in a object history. History contains all the values of my metrics and loss function during the training time. Now I can plot it here directly by passing history to these plot functions. You are seeing this plot already because I am rerunning this system. This was all rerun before I started this session. But I will run it again. What I want to show you is here I'm saving the output to my drive, and you will see that this will come on your local system as well. The thing that we are looking at here is using Google Colab. You can write your results to your disk very easily. So I can this is the result, and it is saved as MLP baseline loss. Let's go and see that it has come to my local or not. As you can see here, we have it on my local. Here it is. Okay. So we learned that we can easily write results to our disk. So the loss is like this. One thing that you might notice is the loss is increasing for the validation data set, which could be due to overfitting or some other issue. We'll come back to it later. And then we are plotting the F1 score. It is one of the accuracy measures. We are getting somewhere less than or around 10% F1 score. And lastly, we are plotting the recall and false positive rate. In this plot, what we are interested to see is the false positive rate should be close to 0 and the recall should be as high as possible. In both of these accuracy plots as well as the loss plot, we are more interested in looking at how the validation data set is performing and not focus much on training. Especially for the accuracy measures, the model, when we fit the model is generally overfitted on the training data. So if we look at the accuracy of the training data, they will generally be inflated. For example, here, the training set has a very high F1 score as compared to the validation set. And this is a misleading information if you rely on it. We do not want to look at training set accuracies to make any judgment on the efficacy of the model. Be very careful about it. Similarly, here in the recall and FPR as well, we are not going to rely on what we are seeing in the training set. For example, here training data is showing very high recall, but that is not representative of the model's true ability. With this, we finish building our baseline MLP model. In the baseline model, we kept the model very simple and we followed few rules of thumb. The baseline model provided us a reasonable first model. Here we are getting F1 score close to 10% and recall of about 7% ish with a very small false positive rate close to 0. This is reasonable. It is not the best, but this shows us that the data does contain some patterns, some predictive patterns, and with a baseline model, we were able to extract them to have some minimal performing system. In the next parts, we are going to see how we can improve further on the baseline model.